Good afternoon, gentlemen. It's been a little while. I ordered some more QBus cards from a fellow in Holland who was getting rid of a bunch of stuff. I've got an 1173 CPU card coming that is compatible with a floating point unit, because there are rumblings that the floating point support in the software floating point support in 211 BSD is a little sketchy, and it requires floating point to run. So that will be handy there, and that'll also leave me with an extra original 1173 card to use for the RSX 11 machine whenever we get it finished in our other backplane. But speaking of the other backplane, since those cards will be here, I'm getting another Ethernet card from the guy too, and a pair of 2 megabyte 22-bit memory cards. So that kind of obviates the need for that SRAM card that I was showing some stuff about before. But we'll get back to that after the H11 is done, and because we'll need a RAM card for the RSX 11 machine that we'll build out of the leftovers from fixing up the H11. So that's not being abandoned. If you want the files so you can finish it before then, I mean, let me know if you're that crazy. Anyhow, so since those cards will be here very soon, I need to get my test rig done. Recall that I was planning to use this, oh shush repeater, I was planning to use this extra backplane with a PC power supply to test all of the cards, so we didn't risk the H11 power supply if something was exceptionally wonky with something. But in order for that to work, we have to generate these signals, these POK signals, to get the CPU card to start. This is based on this tells the CPU that the DC input voltage has stabilized, and it can stop asserting the halt line and begin executing. So there are two lines here. One is DCOK and the other one is POK. And they're both active high, and basically almost as soon as the DC power comes up, DCOK can assert itself, but then, oh shush meter, but then before POK can assert itself, it has to wait at least 70 milliseconds. So we've got two square waves that have to rise one after the other, and we'd experimented with some shit on a breadboard before. This is basically the same thing, except I've increased the resistor value to 47K. I'm still using 10K electrolytic capacitors, and there are two of those Schmidt-Trigger RC circuits in series now, so that the power comes up, it'll wait probably what, 100, 120 milliseconds, I think, somewhere in there, and then one of them will come up, and then 100 or 120 milliseconds after that, the next one will come up after that, which is plenty of time. There isn't any maximum timing requirement on these signals, but there is that minimum timing requirement. And when you turn the power off, it takes a little bit for the capacitors to fully discharge, so if you cycle the power too fast, those timings shrink. That's one of the problems with using RC circuits for CPU reset like we're doing here, but it is a very simple way to do it. Anyway, so let's test this. I've got it set up, I think yes, okay, it's set up to trigger when on the power supply, on the power supply coming on, and then channel 1 is, yes, channel 1 is attached to the first waveform that should assert itself, or the first signal that should assert itself, and then channel 2 is attached to the second one. So let's put it in single mode, and okay, so we're set to 40 milliseconds per division, so yeah, that's 120 milliseconds before the first one comes up, and then more than that, a little more than 120 milliseconds till the second one comes up. So that's fine. Let's cycle the power a little quickly and make sure within a reasonable time everything goes back to normal. Okay, so that was 80 milliseconds there, and that was a pretty fast power cycle. That first signal can come up about as soon as it wants, though, and we've still got plenty of time before that second signal rises that has that at least 70 milliseconds lead time required on it. So I think that's going to work. Let's build that circuit on a piece of perf board, and then we can strap it onto the back plane here somewhere with wire ties or something. Always remember, kids, the bigger the blob, the better the job. Flaws with this circuit. There is no bypass capacitor on this IC. Oh well, whatever. We also should have tied all of our unused inputs to ground, but we didn't. Oh well, whatever. Let's see what happens here now. Alright, I made a stupid mistake and put my power input pin in the wrong place the first time, but I think, hopefully, everything is cool now. Single. Okay. It's still 80 milliseconds. Alright. I think it's working. Let's attach it to the board and slap a CPU in there and see if the CPU initializes. Alright, so the DEC modules don't actually use negative 12 volts, according to the manual. Even the serial card uses some kind of charge pump or something on board to generate negative 8 volts for RS-232 levels, which is a little strange, but alright, whatever. So I think we can get away with just applying 5 and 12 volts here and hooking up a disk drive power connector. Now there's also this plus 5B here. That's for a battery connection, but we're not going to use it. Back in the day, the first PDP-11s used core memory, and core memory keeps its state even when the power is removed from it, and my supposition is that some software relied on that fact, so when they eventually switched to dynamic RAM in these things, MOS RAM, I assume they had to have a battery backup on the RAM so that it could possibly, like keep its state between power cycles so that older software would work right. Or such is my supposition. I may be completely full of shit in that regard. What a kludge. We'll make a real power supply for it later on when the time comes. So watch none of this even frickin' work. Wouldn't that be something? Wouldn't that be something? Now, how are we gonna attach that thing. The holes in my perf board are too small for zip ties. I shall have to use something else. Something hackier. What could ever go wrong with this? Not a thing. It'll be fine. Nothing to worry about. Nothing to worry about at all. Yes. 5 volts off the back plane. We'll stick a connector onto that wire wrap header. 2 5 volts on our board thing. That one right there. Beautiful. Let us double check our handiwork. Ground. 5 volts. 5 volts. 5 volts. Yes. Ground. Okay. Now, number uno thinger is going to be, the first one to come up is DCOK. DCOK is supposed to be this one, I think. I shall double check the backplane manual before I fuck it up. And then POK should be the second one to come up. And that is this one, I believe. Alright. Well, I don't know what to do now other than precariously balance my manual on top of this pile of stuff and get a CPU card in here and see what happens. Here's our 1173 CPU card. Now, it may be worth mentioning that the H11 is unique in that its cards go upside down in the backplane, but all of the digital backplanes, the cards go right side up, component side up, I should say. So let's slot this into slot 1 and hit the juice and see what the blinking lights do. And hope it doesn't smoke the card. Well. Oh, okay, that's D3 and D4, the ones closest to the CPU. Okay, I was worried there for a second. I thought it was telling me that the CPU microcode wasn't running, but that actually means that the module attempted to read the console I/O location and timed out, so there's no serial line unit installed, and it also means that it attempted to read location 0 and timed out, which makes sense since there's no memory installed. So this is a good sign. Here I have a digital 4K memory module that's strapped for segment 0, I think, if I'm reading the documentation right. And here is the Heathkit serial module, which I think is strapped to be the console. So let's fire it up and see what the blinking lights do now. Now, I should note that this is a 22-bit CPU, and these are both 16-bit cards, so I don't think I can actually run the system like this, but hopefully it'll be able to access the serial card and access location 0, and there won't be any error LEDs, if everything's working right. Okay, that's good. It started, but it didn't enter ODT. That's the diagnostic console that replaces the blinking lights. that were on the Unibus PDP-11s. Let me see. Okay, if W3 is installed and W7 is removed, it should go straight into micro ODT. Let's see here. Oh, some of my pins are bent. Figures. The long pins. Now it ought to go on. Alright. Now hopefully D1, that's the one all the way that way, should light, indicating that we've got an ODT console on the serial port. Fucking A, boys. Alright, so I guess the next step is to rig up some kind of shit on this serial card so that I can plug it into a terminal. I'm going to have to check the baud rate settings and stuff on that too. I don't know what it's set to. But anyway, this is excellent. We have our test bed set up, so when the rest of these cards arrive, there's an 1173-AB card coming. Another it's the older Ethernet card, the one that locks up, used to lock up under 211 BSD apparently, but I was reading the patch notes and supposedly they fixed it, but I think it works alright in an RS-H11, which is, we hope. And a Grant continuity card, which I may end up needing while I'm testing shit here, and what was the fourth one? Oh, and those two 2 megabyte memory cards. So with all of that and the Cubone to emulate some floppy drives and this Emulix SCSI controller, we ought to be able to pimp the H11 out really nice and have a pretty cool machine. So, alright, that's it for now. This video has gone on long enough. I'm gonna make me a connectoroo thing here after I slack off a little bit. Maybe, just maybe, we'll see if we can fart around with the ODT console here in a little while. Okay, thank you for joining me, gentlemen. Excellent, excellent, excellent. See you later.